aldehydes and ketones, they have several reactions. The first one is oxidation. We've talked about oxidation in the previous chapter, and we said that oxidation is whenever you either lose a hydrogen or gain an oxygen. We introduced the oxidizing agents, two types of oxidizing agents in there. We introduced a strong oxidizing agent, and strong oxidizing agent like sodium dichromate, Na2Cr2O7, and that normally it dissolved in sulfuric acid and water. We introduced also the Jones reagent, which is the H2CrO3. That is the Jones reagent, and that reagent is nothing but the chromate dissolved in H2SO4, and it creates the chromic acid in here, the H2CO3. Okay, these are strong oxidizing agent, and then you have the mild oxidizing agent that we talked about, which is the pyridinium chlorochromate, PCC, and that needs an organic solvent, which is the dichloromethane, CH2Cl2 in there. Now, whenever your starting material is an aldehyde or a ketone, honestly, it really doesn't matter the strength of the oxidizing agent. So whether the oxidizing agent is strong or mild, your product is going to be the same with the aldehyde in there. So the oxidation definition, as we mentioned, it is the either losing the hydrogen, so you're either losing a hydrogen or you are gaining an oxygen. This is the definition for oxygen in there. This is the definition for oxidation. Here we are actually losing a hydrogen in there, and we are gaining an OH. So when you have an aldehyde and that aldehyde is being oxidized, whether the oxidizing agent is strong or mild, so put this as a note here, it doesn't matter the strength of the oxidizing agent, this one is strong or mild, then your product is going to be the same. The hydrogen of the aldehyde will change into an OH. We're still going to keep the same carbon chain. So I have the same carbon chain in here. I have my carbonyl, but the hydrogen on the carbonyl, that hydrogen will turn into an OH. So here, my product of the oxidation is a carboxylic acid, okay? Because this actually is a carboxylic acid functional group in there. So always aldehydes are oxidized in a strong or mild oxidizing agent to a carboxylic acid. The number of carbons stay the same, everything stays the same, but the hydrogen of the aldehyde turns into an OH, okay? That is it. So the hydrogen turns into an OH. So let's go ahead and highlight that OH in there. Ketones cannot be oxidized. The rule says that with oxidation, I need to lose a hydrogen, and ketones, they have no hydrogen to lose. So ketones can never be oxidized, or cannot. I'm not going to say never because there are exceptions. We're not talking about exceptions here. So ketones, they cannot be oxidized further. So here, this is a ketone. And with ketones and any oxidizing agent, so that is strong or mild, you're going to end up having no reaction. No reaction is NR, okay? It's either like you write no reaction in there, or you go ahead and write what you started with. So you started with a ketone in there, just go ahead and write it as a product. This means that nothing happened to the ketone and the reaction proceeded with actually nothing. So that's why it's a no reaction. This is the oxidation of aldehydes and ketones. So aldehydes can be oxidized into a carboxylic acid. The hydrogen changes into an OH. Ketones cannot be oxidized, and you will have a no reaction. The second type of reaction is reduction. So what is reduction? Reduction is the opposite of oxidation. So remember that we said with oxidation you lose a hydrogen or you gain an oxygen. Well, reduction is the opposite. So with reduction, we're going to add hydrogens to the functional group. Okay, so you look at your functional group and there, what is my functional group for the aldehydes and ketones? It's the carbonyl. So this is it, because both aldehydes and ketones share the carbonyl. So what I'm going to do over here is I'm going to add a hydrogen to this carbon. So we're going to add a hydrogen to this carbon, and we're going to add the hydrogen to the oxygen. It's very simple. So my product in this case is going to show up as a hydrogen being added to the carbon and the hydrogen being added to the oxygen in there. So what I'm going to create in here is basically an alcohol group, because I know that the alcohol has an OH in there. So reduction of carbonyls make an alcohol. And whenever I am reducing carbonyls, it really depends what I'm starting with, because I can manage the type of alcohol that I am creating. Every time I am reducing an aldehyde, my product is a primary alcohol. And if I'm reducing a ketone, my product is a secondary alcohol. To represent reduction, we're going to represent it by an H in brackets in there. So this here means it is a reduction reaction. As we did for oxidation, we represented it by an O, and then it's in brackets as well. There are different types or reagents for reduction. Let's go over them. We have strong and we have weak. Okay, so these two are considered to be strong reducing agents. Okay, and the sodium borohydride, this one is a weak reducing agent. Does it really matter? Well, with aldehydes and ketones, it doesn't. But it's really nice to know which one is strong and which one is weak. With the derivatives of carboxylic acid in the next chapter, yes, it will make a difference, but with aldehydes and ketones, it won't. So the LiAlH4, we call this lithium aluminum hydride. And this is a reagent, a reducing reagent that is water soluble, so it dissolves in water. So let me write it over here. So the LiAlH4, this is called lithium aluminum hydride reagent, and the NaBH4 is called sodium borohydride reducing agent. Okay, and then we have the regular hydrogen in presence of Pt. So both of those are strong. The sodium borohydride is a weak reducing agent. We represent all of those as an H. So whenever you see that H in there, we don't care about it. It can be any one of those. Any one of those. The lithium aluminum or the hydrogen or the sodium borohydride. Any one of those. Okay? So that's your reducing agent. And the rule says that whenever you are doing any reduction reaction, it's very simple. All what you need to do is just go ahead and highlight your functional group. Okay? Because your addition is going to be on the functional group. So what do I have here? I have the carbon and I have the oxygen. So what you're going to do here is you're going to add a hydrogen to this carbon, add a hydrogen to the carbon, and add a hydrogen to the oxygen. This is it. Okay? And add a hydrogen here. That is for the reduction. It's important to know what you are starting with so that to know what you're going to end up with. Here you're starting with a ketone. So I know that ketones with reduction, I'm going to end up having a secondary alcohol. So all what you need to do is draw your product. I am not adding any carbon. So I am starting with a 3-carbon chain. I'm going to end up with a 3-carbon chain in here. Okay? So what I did is I simply added a hydrogen on this oxygen, and I added a hydrogen here. This is what I did. I added the hydrogen and the oxygen in there, and I ended up forming a secondary alcohol. If you want to go ahead and write it down as a skeletal form, you don't have to show the addition of the hydrogen. So you just show the OH that you're forming. You don't have to show that you added a hydrogen over there. And that is a secondary alcohol that you are making in this case. Okay. Same thing. I do have a ketone. I'm starting with a ketone. So it will really help if you go ahead and you highlight your functional group so that you know that the addition is going to be on this carbon and on the oxygen. So you're going to add a hydrogen to this carbon and you're going to add a hydrogen to this oxygen, and your product is going to be a secondary alcohol. So you're going to be an OH over here and you added a hydrogen in there. Okay. Your product should not show any carbonyl because you're adding to the carbonyl. You are making 2 sigma bonds. These are the 2 sigma bonds between the carbon and the hydrogen and the oxygen and the hydrogen, and you are breaking the pi bond. So you can show it as a skeletal form, and that is going to be the OH, and this one is still going to be a secondary alcohol. Again, if you specify the reducing agent, it really doesn't matter with the aldehydes and ketones. Any reducing agent can do the job. Just you have to know that this is a reducing agent, but please make yourself familiar with those reagents in there. So this is a reducing agent, and that reducing agent now is going to, again, reduce the carbonyl. Now I am working with an aldehyde. So I know that aldehydes, so this one is an aldehyde and this one is an aldehyde as well. So I know that aldehydes should be reduced into a primary alcohol. So look here, aldehydes are reduced into a primary alcohol. So my product is going to be a primary alcohol. I'm going to add a hydrogen here and a hydrogen there. This is what I'm going to do, okay? So let's go ahead and write it down exactly as you see it. I no longer have a carbon double bond O. I still have an oxygen. I'm going to add a hydrogen here and I'm going to add a hydrogen there. I already had a hydrogen. Okay, so that I'm going to end up having this carbon being a CH2 and an OH. This is a primary alcohol there. So this is going to be a primary alcohol. You can take out the hydrogens if you want and represent it as a primary alcohol like that. So these two are the same, and this one is a primary alcohol. It's a primary alcohol as well. Okay. Same thing over here. I'm going to add the hydrogen here and the hydrogen there, and I'll end up forming my oxygen. I added a hydrogen here. And on this carbon, I added a hydrogen, and I already had a hydrogen. So this is exactly the same as this. And these two are primary alcohols. Okay, so again, when you are reducing, aldehydes turn into primary alcohols. Ketones, they turn into a secondary alcohol. No matter what reducing agent you use, there are 3 reducing agents that we can use to perform the reduction of aldehydes and ketones.